In the name of Almighty God, I'm Mahsa Sankasha, and today I want to talk about piezoelectric energy harvester. A piezoelectric energy harvester is a device that converts mechanical energy such as vibrations or pressure into electrical energy using the piezoelectric effect. These devices are used to power small electronic sensors and other devices by capturing otherwise wasted energy from sources like traffic, human movements, or industrial machinery. They are useful in applications that require a reliable battery-free power source for remote or hard-to-reach locations. And how it works. The first step is the piezoelectric effect. The core principle is the direct piezoelectric effect, where certain materials such as like crystals or ceramics generate an electrical charge when subjected to mechanical stresses. And the next step is conversion process. When the harvester is subjected to a force like a vibration, the piezoelectric material deforms, creating a voltage and a flow of electrical charge, such as this simulation. And the next step is powering devices. This generated electricity can then be used to charge a battery or supercapacitor or to directly power a small device such as sensors. And what about the key features and advantages of waste energy conversion? Harvesters turn wasted mechanical energy into usable power. And the next one is reliability and robustness. They offer a reliable and robust power source, especially for applications where frequent battery replacement is not feasible. And compact and scalable. They can be small and compact, making them suitable for integration into micro electromechanical systems or MEMS. And the next one is environmental tolerance. Many piezoelectric generators are unaffected by environmental conditions like humidity. And what about the applications? Self-power sensors, powering wireless sensors, including those used for monitoring structural health in buildings or bridges. And the next one is variable devices, generating power from human motion to operate variable. The next one is automotive, powering sensors inside tires or to monitor pressure, eliminating the need for batteries. The next one is aerospace and industrial, providing power for systems in remote or harsh environments such as in oil drilling or in aircraft. Roadway energy harvesting, capturing energy from the weights of traffic on highway and sidewalks to generate electricity. And the next one is energy harvesting. Energy harvesting, also known as power harvesting, energy scavenger or ambient power, is a process by which energy is derived from external sources, for example, solar power, thermal energy, wind energy, salinity gradients, and kinetic energy, also known as ambient energy, then stored for use by a small wireless autonomous devices like those used in wearable electronics, condition monitoring, and wireless sensor networks. Energy harvesters usually provide a very small amount of power for low-energy electronics, while the input fuel to some large-scale energy generation costs resources, oil, coal, and etc. The energy source for energy harvesters is present and as ambient background. For example, temperature gradients exist from the operation of a combustion engine, and in urban areas, there is a large amount of electromagnetic energy in the environment due to radio and television broadcasting. One of the first examples of ambient energy being used to produce electricity was the successful and useful use of electromagnetic radiation or EMR to generate the crystal radio. The principles of energy harvesting from ambient EMR can be demonstrated with basic components. And what about the operation? Energy harvesting devices converting ambient energy into electrical energy have attracted much interest in both the military and commercial sectors. Some systems convert motion, such as that of ocean waves, into electricity to be used by oceanographic monitoring sensors for autonomous operation. Further and future applications may include high power output devices or array of such devices deployed at remote locations to serve as reliable power stations for large systems. Another application is in wearable electronics, where energy harvesting devices can power or recharge cell phones, mobile computers, and radio communication equipment. And all of these devices must be sufficiently robust to endure long-term exposure to hostile environments and have a broad range of dynamic sensitivity to exploit the entire spectrum of wave motions. In addition, one of the latest techniques to generate electric power from vibration waves is the utilization of acoustic boosters. This method falls under the category of piezoelectric-based vibration energy harvesting, where the harvested electric energy can be directly used to power wireless sensors, monitoring cameras, and other Internet of Things or IoT devices. And the chapter of accumulating energy. Energy can also be harvested to power small autonomous sensors, such as those developed using MEMS technology. These systems are often very small and require little power, but their applications are limited by the reliance on battery power. Scavenging energy from ambient vibration, wind, heat, or light could enable smart sensors to function indefinitely. Typical power densities available from energy harvesting devices are highly dependent upon the specific applications, affecting the generator size and the size design itself of the harvesting generator. In general, for motion power devices, typical values are a few microwatts per centimeter cubic for human body powered applications and hundreds of microwatts per centimeter cubic for generators powered by machinery. Most energy scavenging devices for wearable electronics generate very little power. And what about the storage of power? In general, energy can be stored in a capacitor, supercapacitor, or battery. Capacitors are used when the application needs to provide huge energy spikes. Batteries leak less energy and are therefore used when the device needs to provide a steady flow of energy. These aspects of the battery depend on the type that is used. A common type of battery that is used for this purpose is the lead acid or lithium-ion battery. Although older types such as nickel metal hydride are still widely used today. Compared to batteries, supercapacitors have virtually unlimited charge-discharge cycles and can therefore operate forever, enabling a maintenance-free operation in IoT or Internet of Things and wireless sensor devices. And the chapter of use of power. Current interest in low-power energy harvesting is for independent sensor networks. In these applications, an energy harvesting scheme put power stored into a capacitor, then regulates it to a second storage capacitor or battery for use in microprocessor or in the data transmission. The power is usually used in a sensor application and the data is stored or transmitted, possibly through a wireless method. And what about the motivation? One of the main driving forces behind the search for new energy harvesting devices is the desire to power sensor networks and mobile devices without batteries that run on intermittent computing systems and need external charging or service. Batteries have several limitations such as limited lifespan, environmental impact, size, weight, and cost. Energy harvesting devices can provide an alternative or complementary source of power for applications that require low power consumption, such as remote sensing, wearable electronics, condition monitoring, and wireless sensor networks. Energy harvesting devices can also extend the battery life or enable batteryless operation of some applications. Another motivation for energy harvesting is the potential to address the issue of climate change by reducing greenhouse gas emissions and fossil fuel consumption. Energy harvesting devices can utilize renewable and clean sources of energy that are abundant and ubiquitous in the environment, such as solar, thermal, wind, and kinetic energy. Energy harvesting devices can also reduce the need for power transmission and distribution systems that cause energy losses and environmental impacts. Energy harvesting devices can therefore contribute to the development of a more sustainable and resilient energy system. Recent research in energy harvesting has led to the innovation of devices capable of powering themselves through user interactions. Notable examples include battery-free Game Boys and other toys, which showcase the potential of devices powered by the energy generated from user action, such as pressing buttons or turning knobs. These studies highlight how energy harvested from interactions can not only power the devices themselves but also extend their operational autonomy, promoting the use of renewable energy sources and reducing reliance on traditional batteries. And the chapter of energy sources. There are many small-scale energy sources that generally cannot be scaled up to industrial size in terms of comparable output to industrial size solar, wind, or wave power. Some wristwatches are powered by kinetic energy called automatic watches, generated through movement of the arm when walking. The arm movement it causes winding of the watch's mainspring. Other designs like Seiko's kinetic use a loose internal permanent magnet to generate electricity. Photovoltaics is a method of generating electrical power by converting solar radiation into direct current electricity using semiconductors that exhibit the photovoltaic effect. Photovoltaic power generation employs solar panels composed of a number of cells containing a photovoltaic material. Photovoltaics have been scaled up to industrial size and large-scale solar farms now exist. Thermoelectric generators consist of the junction of two dissimilar materials and the presence of the thermal gradient. High voltage outputs are possible by connecting many junctions electrically in series and thermally in parallel. Typical performance is 100 to 200 microvolt per Kelvin per junction. These can be utilized to capture milliwatts of energy from industrial equipment, structures, and even human body. They are typically cooled with heat sinks to improve temperature gradient. Microwind turbines are used to harvest kinetic energy readily available in the environment in the form of the wind to fuel low power electronic devices such as wireless sensor nodes. When air flows across the blades of the turbine, a net pressure difference is developed between the wind speeds above and below the blades. This will result in a live force generated which in turn rotates the blades. Similar to photovoltaics, wind farms have been constructed on an industrial scale and are being used to generate substantial amount of electrical energy. Piezoelectric crystals or fibers generate a small voltage whenever they are mechanically deformed. Vibration from engines it can stimulate piezoelectric materials as can the heel of a shoe or the pushing of a button. Special antennas can collect energy from stray radio waves. This can also be done with a rectangle and theoretically at even higher frequency EM radiation with an antenna. Power from keys pressed during use of a portable electronic device or remote control using magnet and coil or piezoelectric energy converters may be used to help power the device. Vibration energy harvesting, based on electromagnetic induction, uses a magnet and a copper coil in the most simple versions to generate a current that can be converted into electricity. Electrically charged humidity produces electricity in the Ergen, a nano pore based device invented by a group at the University of Massachusetts at Amherst, led by Jun Yao. And what about the chapter of ambient radiation sources? A possible source of energy comes from ubiquitous radio transmitters, historically either a large collection area or close proximity to radiating wireless energy source is needed to get useful power levels from this source. The antenna is one proposed development which would overcome this limitation by making use of the abundant natural radiation such as solar radiation. One idea is to deliberately broadcast radio frequency energy to power and collect information from remote devices. This is now commonplace in passive radio frequency identification or RFID systems, but the Safety and U.S. Federal Communications Commissions and equivalent bodies worldwide limit the maximum power that can be transmitted this way to civilian use. This method has been used to power individual nodes in a wireless sensor networks. Various turbines and non-turbine generator technologies can harvest airflow toward wind turbine and airborne wind energy systems harness the flow of air. Multiple companies are developing these technologies which can operate in low light environments such as HVAC ducts and can be scaled and optimized for the energy requirements of specific applications. The flow of blood can also be utilized to power devices. For example, a pacemaker developed at the University of Bern used blood flow to wind up a spring, which then derives an electrical microgenerator. Water energy harvesting has seen advancement in designs such as generators with transistors like architecture achieving high energy conversion efficiency and power density. And what about the photovoltaic? Photovoltaic energy harvesting wireless technology offers significant advantages over wired or solarly battery-powered sensor solutions, virtually inexhaustible sources of power with little or no adverse environmental effects. Indoor PV harvesting solutions have to date been powered by specially tuned amorphous silicon, a technology most used in solar calculators. In recent years, new photovoltaic technologies have come to the forefront in the energy harvesting, such as dye-synthesized solar cells. The dyes absorb light much like chlorophyll does in plants. Electrons released on impact escape to the layer of TiO2 and from there diffuse to the electrolyte. As the dye can be tuned to the visible spectrum, much higher power can be produced. And the chapter of piezoelectric. The piezoelectric effect converts mechanical strain into electric current or voltage. This strain can come from many different sources: human motion, low frequency seismic vibrations, and acoustic noise are everyday examples. Except in rare instances, the piezoelectric effect operates in AC, requiring time varying inputs and mechanical resonance to be efficient. Most piezoelectric electricity sources produce power on the order of milliwatts to small for system applications, but enough for handheld devices such as some commercially available self-feeding wristwatches. One proposal is that they are used for micro-scale devices such as in a device harvesting microhydraulic energy. In this device, the flow of pressurized hydraulic fluid drives a reciprocating piston supported by three piezoelectric elements, which converts the pressure fluctuations into an alternating current. Piezoelectric energy harvesting has been investigated only since the late 1990s. It remains an emerging technology. Nevertheless, some interesting improvements were made with a self-power electronic switch at an INSA School of Engineering implemented by a spin of Albany. In 2006, the proof of concept of a battery-less wireless doorbell push button was created, and recently a product showed that classical wireless wall switch can be powered by a piezo harvester. Other industrial applications appeared between 2000 and 2005 to harvest energy from vibration and supply sensors, for example, or to harvest energy from shock. Piezoelectric systems can convert motion from the human body into electrical power. DARPA has funded efforts to harness energy from leg and arm motion, shoe impacts, and blood pressure for low-level power to implantable or wearable sensor. The nano brushes are another example of piezoelectric energy harvester. They can be integrated into clothing. Multiple other nanostructures have been exploited to build an energy harvesting device. For example, a single crystal PMNPT nanobelt was fabricated and assembled into a piezoelectric energy harvester in 2016. Careful design is needed to minimize user discomfort. These energy harvesting sources, by associating affect the body. The vibration energy scavenger project is another project that is set up to try scavenging electrical energy from environmental vibrations and movements. Microbelt can be used to gather electricity from vibration respiration. Besides, as the vibration of motion from human comes in three directions, a single piezoelectric cantilever based omnidirectional energy harvester is created by using internal resonance. Finally, a millimeter scale piezoelectric energy harvester has also already been created. Piezoelements are being embedded in walkways to recover the people energy of footsteps. They can also be embedded in shoes to recover walking energy. Researchers at MIT developed the first micro-scale piezoelectric energy harvester using thin film PZT in 2005, and Hodgson and Cook invented the ultra-wide bandwidth micro-scale piezoelectric energy harvesting device for exploiting nonlinear stiffness of a doubly clamped electromechanical systems or MES resonator. The stretching strain in the doubly clamped beam shows a nonlinear stiffness which provides a passive feedback and results in amplitude stiffened doffing mode resonance. Typically, piezoelectric cantilevers are adopted for above-mentioned energy harvesting system. One drawback is that piezoelectric cantilever has gradient straight distribution. For example, the piezoelectric transducer is not fully utilized. To address this issue, triangular shape and N-shape cantilever are proposed for uniform strain distribution. In 2018, Suzhou University researchers reported hybridizing a turboelectric nanogenerator and a silicon solar cell by sharing a mutual electrode. This device can collect solar energy or convert the mechanical energy of falling raindrop into electricity. UK telecom company Orange UK created an energy harvesting t-shirt and boots. Other companies have also done the same. And what about the energy from the smart roads and piezoelectricity? Brothers Pierre Curie and Jacques Curie gave the concept of piezoelectric effect in 1880. Piezoelectric effect converts mechanical strain into voltage or electric current and generates electric energy from motion, weight, vibration, and temperature change as shown in the figure. Considering piezoelectric effect, the thin film lead Sequonaut, Titanite, PZT, micro electromechanical systems or MEMS, power generation and generating device has been developed. During recent improvement in piezoelectric technology, AXA researcher differentiated two modes called and in vibration converters and redesigned to resonate as a specific frequency from external vibration energy source, thereby creating electrical energy via the piezoelectric effect using electromechanical damped mass. However, AXA further developed beam structure electrostatics devices that are more difficult to fabricate than PZT MEMS devices versus a similar because general silicon processing involves many more mask steps that don't require PZT. Piezoelectric type sensors and actuators have a cantilever beam structure that consists of a membrane bottom energy harvesting the collection of a small amount of ambient energy to power wireless devices is a very promising technology for applications where batteries are impractical, such as body sensor networks and inaccessible remote systems. The performance and potential of energy harvesting devices depend strongly on the performance and specific properties of materials. In this chapter, the important properties and potential of materials used in energy harvesting devices are reviewed. An introduction to the concept of energy harvesting is given with a special discussion on motion energy harvesting limits. The state-of-the-art of materials for piezoelectric, electrostatic, thermoelectric, and electromagnetic harvesting devices is discussed, with emphasis on desired material properties and corresponding available materials. In addition to the materials required in the energy transduction mechanism itself, the performance of mechanical oscillators at small scales is a critical factor in motion energy harvesting. For this reason, material requirements, performance, and limitations for the implementation of a low frequency and broadband mechanical oscillators are reviewed in the final section of this chapter. Energy harvesting is a promising technique that can help produce renewable and clean energy and improve sustainability of infrastructure. The objective of this simulation is to review available energy harvesting techniques that are used for roadway and bridge for different applications, including photovoltaic cell, solar collector, geothermal, thermoelectric, electromagnetic, and piezoelectric systems. The energy harvested and can produce electrical energy, provide heating or cooling, ice melting, power wireless sensors, and monitor structure conditions. Each energy harvesting technology is examined in depth, including working principles, applications, examples, prototype development, and the major findings reported in the literature. The review summarized previous study efforts on energy harvesting systems in the areas of material design, system optimization, theoretical analysis, laboratory testing, field experimental and numerical modeling. Different energy harvesting technologies were compared in terms of power output, cost effectiveness, technology readiness level, advantages and disadvantages, support from government and on industry. Finally, future research recommendations of energy harvesting in roadway and bridge were proposed. Energy harvesting is a promising technique that can help to solve the global energy challenge without depleting natural resources as one of the green energy solutions. Energy harvesting can reduce greenhouse gas emissions generated with traditional energy sources. Piezoelectric, thermoelectric, electromagnetic, and photovoltaic techniques are some examples of energy harvesting technologies that can be used to collect energy from the ambient environment to generate electricity nowadays. These technologies work in the different principles and thus have different applications requirement and energy conversion efficiency. The roadway is designed to provide serviceability and durability under repeated traffic loading and climate conditions. The pavement deforms under truck loads and experiences high temperature in summer, due to solar radiation. There are many opportunities to collect waste, kinetic energy, vibration, and deflection, and etc. And environmental energy such as solar, heat, and etc. from the roadway environment. In particular, mechanical energy can be converted into the electricity via stress or vibration using piezoelectric transducers placed on pavement surface or embedded in the pavement. It is projected that truck traffic will continuously grow in the highway network of the United States due to the desire of economic development for freight transportation. Therefore, there is a high potential to harvest kinetic energy from the pavement using piezoelectric materials. This chapter provides a comprehensive review on the topic of piezoelectric energy harvesting from pavement. Various transducer design and piezoelectric energy harvesting systems are introduced, and their advantage and disadvantage are compared. The previous work that studied piezoelectric energy harvesting in the pavement was synthesized, including theoretical analysis, laboratory tests, and field trial. Different ways of using the harvest energy are discussed. Finally, the challenge and recommendations for future studies are provided. And the challenge of power electronics control system energy harvesting. Energy harvesting is a process by which energy is collected and stored from the environment. Energy can be captured from a number of sources: solar power, salinity, gradient, thermal energy, kinetic energy, wind energy, nuclear radiation, and radio frequency are some possibilities to scavenge energy to power embedded systems. And here you can see that in the component I have used three different physical module, solid mechanics, electrostatic and electrical circuit, and the geometry and the material is a lead silicon titanium and structure scheme. In the lead silicon, you can see stress and strain for charge form, and in the stress charge and the structural steel is another type of material. You can see the Young modulus, elastoplastic, Ludwig Johnson Cook, Swift was Hackett, Shelby, Armstrong, Norton, and etc. And the mesh we have used is triangular, free triangular. And the study we have used is frequency response, load dependence, acceleration dependence. And you can see that we have a stress based on Newton per square meter, electrical field based on volt, electric field. The first one was electropotential. Here is the electrovolt. The plot for frequency response, voltage power, and load dependence voltage power and acceleration dependence voltage power. Thank you so much for watching my video until the end. And also you can download this computer simulation from github.com /mahsascript /piezoelectric _ energy _ harvester.